Irodov problem number 3.12. Electric field on the axis of a non-uniform ring. Now the problem is saying that a thin non-conducting ring of radius r has a linear charge density lambda is equal to lambda naught cos phi, where lambda naught is a constant and phi is the azimuthal angle. Find the magnitude of the electric field strength, part A, at the center of the ring, and part B on the axis of the ring as a function of the distance x from its center. Investigate the obtained function at x is much greater than r. So basically in the present problem, we have a ring, and on the ring, the linear charge density lambda varies with the azimuthal angle. So we know azimuthal angle is the property of a point on the ring. So if lambda is varying with azimuthal angle, it means lambda has a continuous variation on the ring. So we have to apply the concept of calculus. Already we have seen in the fundamental lecture what is the azimuthal angle and how we can take the element dq on the ring when lambda is a function of azimuthal angle phi. So before proceeding with the solution of this problem, let me make a short recap of the skill needed in this problem, that is the 3D visualization of the components of the electric field. Okay. So this skill we already covered in our basic fundamental lectures. Suppose we have a ring of radius r in the xy plane. Okay. So this is not the solution of this problem. Here I'm telling you the skill which will be needed in this problem. So if you are clear with the skill, you will be very comfortable with the problem. Okay. So this is the ring which is located in xy plane. Okay. This is the plane of the ring which I'm labeling as x and y. And z axis I'm taking along the axis of the ring. Okay. So this is the coordinate system. XY plane is taken in the plane of the ring and z axis is along the axis of the ring. Got it? So say this point is the center and there is a point P, say on the axis of the ring. And we all know what is azimuthal angle. Already we covered in the basic lecture. Azimuthal angle is the angular coordinate of the point on the ring with respect to some reference line or reference diameter. So if I'm taking the x-axis as the reference line and there is a point P, so this angle will be the azimuthal angle for point P, okay, and say there is a charge Q at this location. Okay, already I'm taking this point P here, so let this point be O. So a point charge Q is located at a point O which with azimuthal angle phi. Got it? So for each, if you are rotating Q on the ring, phi will be changing, correct? If you are rotating Q on the ring, suppose Q is a bead which can be rotated on the ring. So for each changing position of the point charge Q, angle phi will be changing, correct? If you are making the top view, suppose you are observing from the top of the ring, so you will see something like this. This is x-axis and this is y-axis, correct? And this will be your z-axis dot coming towards you, and this is the azimuthal angle which is phi. Of course, phi will be present in the plane of the ring, and this is a charged particle Q at a position O, correct? This is the top view. So as I told you, if Q is being rotated along the ring, phi will be changing. So for each point of the ring, phi will be changing, and the value of phi will be between 0 and 2 pi. This we already did in the basic fundamental lectures. Okay. Now suppose you have to find the electric field of this point charge at a point P on the axis of the ring. What is the distance of the point P? There is a point P on the axis of the ring at a distance z from the center of the ring. Okay. So you have to find the electric field due to the point charge Q on the axis of the ring at a point P, and the distance of P from the center is z and r is the radius of the ring. So this distance is how much? R. Okay. So we know the basic for finding the electric field due to a point charge at any target point. You make a line joining the target point with the source. In this case, the source is the point charge Q. So I'm making a line joining P with Q. So your electric field vector will be along this line OP, and this will be like this, correct? So this is your electric field vector E. Okay. Now what will be the magnitude of vector E? So you can write vector E as the Coulomb's constant K, the source Q, and this distance is R divided by R square, correct? And of course your R will be what? R will be, if you apply the Pythagoras theorem, this is a right angle triangle. So you'll get capital R square plus Z square under root. This will be the value of R. Okay. Now let's see, if you take the component of the electric field vertically and horizontally. So say here I'm duplicating the XY plane. Say I'm duplicating the plane of the ring. That means I'm making a plane parallel to the plane of the ring. What did I making? A plane parallel to the plane of the ring, something like this. Plane parallel to plane of ring. And I can duplicate the axis too. So this will be your x-axis and this will be your y-axis, correct? X-axis is parallel to the initial x-axis, y is parallel to initial y-axis. Now if you see, how we will find the component of vector E in the horizontal plane? So say the line OP makes an angle theta with the plane of the ring. Let theta be the angle subtended by line OP with plane of ring, that is XY plane. Okay. So if you want to indicate theta in this figure, I guess you will be able to make theta. This is the line OP and this is the XY plane. So this angle will be theta. See the difference between theta and phi. Theta is the angle subtended by the line OP with the plane of the ring. Phi is the azimuthal angle. That is, phi is in the plane of the ring. If you see the top view, in the top view, you can visualize phi, but you cannot visualize theta. Correct? In the top view, you can visualize phi, but you cannot visualize theta. Now, if you are making this triangle, which PCO, if you are making a triangle PCO, which is a right angle triangle, right? This is P, this is C, and this is O. So this is the plane of ring. This is Z, this is R, and this angle is theta. And this is how much? Small r, that is capital R square plus Z square under root. So this, in this triangle, you can visualize the angle theta. Okay. Now, if theta is the angle made by the line OP with the plane of the ring, that is with the XY plane, and the electric field because of the point charge Q is along the line OP, can you tell me what will be the angle subtended by the electric field with the XY plane? So you'll say, if this angle is theta, so electric field vector will also subtend an angle theta with the XY plane, correct? Because these will be the corresponding angle, correct? So you can say vector E subtends angle theta with XY plane. Got it? Now, if you take the component of E now, where one component in the vertical direction, that is along the Z axis, and one component in the horizontal direction, that is along the XY plane. So if this angle is theta, your vertical component will come to be how much? Your vertical component will come to be E sine theta, correct? It will come to be, I'm making it with yellow color, E sine theta, and your horizontal component will come to be how much? E cos theta. So this will be E cos theta and this will be E sine theta, correct? Now E cos theta is coming in which plane? In the horizontal plane, that is in the xy plane, and E sine theta is coming along the z axis. So if you see the top view, we are basically visualizing a three-dimensional component case in 2D plane or 2D plane of paper. So just have a very clear visualization. Your electric field is going like this. Are you getting the point? It is emerging out from P. And if it is like, suppose if in this case, I tell you, try, suppose just pick up your pen and take a notebook and make a circle. Just try it out, okay? Literally try it out to have a better understanding. Make a circle, make x-axis, make y-axis, make a point charge Q, and make a point P here. And take a pen, and suppose your pen is representing the electric field vector. Your pen is representing the electric field vector. Now place the tail of the pen, that is this bottom of the pen, at a point P. Okay, so what do you think? I'm just giving you three options. Tell me which orientation of the pen will be correct. Will the pen, this pen is representing the electric field vector, okay? This pen which you are holding in your hand is representing the electric field vector. So if you're placing the pen like this, perpendicular to the plane of paper, say option A, pen is perpendicular to the plane of paper, will it be correct orientation of electric field? And option B, pen is like this, the whole pen is in the plane of paper, will it be the correct orientation? Pen is in plane of paper, will it be correct orientation? Or option C, the pen is like this, the tail of the pen is at a point P and it is little bit tilted, it is along the line OP, pen is going along the line OP, but it is little bit elevated from the paper, something like this. So will this option be correct? So what do you think? Just make the video still. Pen is along OP and elevated with respect to paper. So what do you think? Which orientation will be the correct orientation for the pen or the electric field vector? Okay, just still make the video still and check out your answer. So the correct answer is what? The correct answer is option C. Correct, this is wrong option. The electric field won't be perpendicular to the xy plane. See, it is tilted. This orange color is the electric field. This orange color vector is the electric field which is along the line OP. Correct? The pen is not in the plane of paper. The orange color vector, electric field vector, is not in the xy plane. So this option is also incorrect. The orange vector is tilted with respect to xy plane. Correct? And what is the angle subtended by the pen with the plane of the paper? Your plane of paper is representing the plane of the ring. Correct? Your plane of paper where you made the circle is representing the plane of the ring or the xy plane. So what is the angle? What do you think your pen is making with the plane of the paper? So same angle which the electric field is making with here the plane of the ring or xy plane, that angle is theta. So your pen would be making an angle theta with the xy plane. Correct? Now tell me one thing. If you are sliding discharge Q on the ring, say you are rotating discharge Q on the ring like this, okay, the charge Q is being rotated on the circumference or periphery of the ring. So what do you think? Phi will be changing or not? What do you think? Phi will be changing or not? Yes, of course, phi will be changing, because for each point on the circumference of the ring, the azimuthal angle will be changing from 0 to 2 pi. And what do you think? Theta will be changing or not? No, theta will not be changing. Theta will remain constant, correct? Because your line joining the point P with the charge Q and charge is on the circumference, this orientation is not changing. It is like in the conical form. So theta will remain constant. So if you are rotating Q on the circumference, phi will continuously be changing, theta will not change. Got it? Now we have to make the component. Now we have to make the projection or components. Now be very much clear about drawing the components. Whenever you make the component or projection of the vector, it is a shadow of the vector. So it is made just below the vector. If the light falls, the vector acts as a barrier for the light. So the shadow is created below the vector. So when you are making the projection of E in the xy plane, that is coming to be E cos theta. So that projection will be made along the line OP, correct? Along the line OP. So this E cos theta will be like this. This is the component E cos theta. And another component which is coming along the z axis is E sin theta. So E sin theta is giving you Ez, the z component, and E cos theta is giving you the component in the xy plane, Exy. Got it? So this is how we can find the two components. One component in the xy plane, which is E cos theta, which is just below the vector E, that is along the line OC or OP. If you see from above, O is a point, below I can write here O dash. O dash is a point just above O, right? The corresponding point of O, which is in the above plane. So O and P and C will be a point below P. So your this component E cos theta will be along this line, and E sin theta is coming outward. Okay. Now if this angle is phi, this angle will also be phi. Now if you want to take the x component and y component, then you have to further resolve the component E cos theta, correct? So if I'm resolving the further E cos theta, if I'm just focusing on what? XY plane, and this is E cos theta and this angle is phi. So I have to take further, because E cos theta is neither the x component nor the y component, it is a component in the xy plane. So if we want to take the further components, we have to further resolve it. So this will come to be the length of the vector E cos theta cos phi, and this component will give you Ex, and this component will be the length of the vector E cos theta sin phi, correct? And this component will give you the component along the y-axis. Now you got the three component, correct? This is the x component, this is the y component, this is the z component. So this is how we can find the three dimensions components of the electric field. Okay, so this is the approach we are going to employ in the present problem. The only difference is in this case you have taken a discrete isolated point charge. In the case of a ring, the point charges will be continuously distributed. So instead of Q, we will be taking what? An elemental charge dq. Rest of the approach will be the same. Got it? Now let's see Irodov 3.12. Here we have a case of a non-uniformly charged ring, because lambda depends on the azimuthal angle that makes the ring non-uniformly charged. And we have to find the electric field on the axis at a distance x from the center. Okay. So already we did in basic lectures what is the electric field on the axis of a uniformly charged ring, but there was a case of a uniformly charged ring. Okay. Now here the ring is non-uniformly charged, and we have to find two parts. In first part we have to find the field at the center, and in the second part we have to find the field on the axis of the ring as a function of the distance x from the center. So of course we will do first part first. But here, your first part can also be obtained as the special case of second part, correct? What you can do, you can also do the second part first, because you know second part is a generalized case at any distance x from the center. So when you're finding at the center, simply put x is equal to 0. So this part can also be solved as a special case of part B when x is equal to 0. However, I'm solving first part as an individual part. Okay? And we'll see in the second part, if we put x is equal to 0, whether we'll get it part A answer or not. So say this is the plane of the ring, and I'm taking, since the x is given along the axis of the ring, the distance x is given as a distance on the axis of the ring. So to maintain little sophistication, what we can do, we can take that axis as x-axis, and we can take this as y-axis and x cross y, this as z-axis. Got it? And say this I'm taking as the reference line, and this is the charge element, because we have to take a charge element because lambda is varying with azimuth. So this is g phi and this is phi, this is L and this is a dl, and say it has a charge dq, correct? So we have to find the field at the center. So only 2 dimensions will be involved in part A. There is no need for 3 dimensions. So part A is relatively easier than the skill we did right now. So this element can be treated as a point charge, and the field will be like this, say dE, correct? Now what will be the magnitude of dE? So this distance is r, so we can write dE as Coulomb's constant k dq by r square. So k and dq we know, we have done in basics. Dq will be lambda dl by r square, that is k lambda, and dl is what? It's a circular arc d phi, so I'll get r d phi by r square, so I'll get k lambda d phi divided by r. So this came to be the magnitude of electric field, and I'm taking an outward model, so I'm not putting this lambda in modulus since I'm making the outward model. And in basics we have seen, when you are making the field outward, simply you have to keep the source charge as it is. If you are making inward, you have to keep the source charge with a reversal sign. So here I'm making the outward model, so I'm putting it simply lambda, okay, dq. Now we have to take the component of this dE. So this angle is phi, this angle will also be phi, correct? So if I'm taking the component, so I can drop the perpendicular. So this will come to be dE sine phi, and this will come to be dE cos phi, correct? Where phi is the azimuthal angle. So what is dE? Sorry, this is your dE. So what is your dEx? The component of dEx is 0 because x-axis is perpendicular to the plane of paper. There is no component. What is your dEy? On the y-axis we have dE cos phi. Phi is the azimuthal angle, and with a negative sign because it is pointing downward. So I will have minus k lambda d phi by r cos phi, correct? Now if you want to find Ey, we have to integrate. We know vector integral is done along different axes. So I will have minus k lambda d phi cos phi divided by r. Now we cannot bring lambda outside because in this present problem lambda is a function of azimuth. So lambda is given to be lambda naught cos phi. So I'll have minus k lambda naught cos phi d phi cos phi divided by r. Okay, now whatever are the constants can be taken out. So Ey will be minus k lambda naught by r. What is left is cos square phi d phi integral, and we will put the limit of phi 0 to 2 pi. And I told you how to integrate this thing even in my lecture of variable linear charge density, the link of which is given in the description. You can find this integral cos square phi d phi. So I can write as 1 plus cos 2 phi by 2 d phi. That is a basic trigonometric formula. So I'll get half d phi plus cos 2 phi d phi, correct? So you will get it what? You will get half, and the integral of d phi is phi, plus the integral of cos 2 phi is sine 2 phi, and we have to divide by the coefficient of phi, that is 2. Now you can put the limit phi 1 to phi 2. So I can use this integral in this case. So I'll get this thing as what? You will get minus k lambda naught by r, and you will get into half phi. Okay, then you will get what? Plus sine 2 phi by 2 plus sine 2 phi by 2, and within the limits phi 1 begins with 0, phi 2 ends at 2 pi. So you will get Ey is minus k lambda naught by 2r 2 pi minus 0, that is the limit of phi, plus I can take half common, sine 2 into 2 4 pi minus sine 0, and we know sine n pi, n is any integer is 0. So this will be 0, this will be 0. So there will be no contribution of the second term. So your answer will be Ey is minus k lambda naught 2 pi by 2r. 2 will get cancelled away. You will get minus k lambda naught pi by r. Okay, this is the value of Ey. Okay, this is the component along the y-axis. Okay, now what is left? I guess the component along the z-axis. Okay, now let us find dEz. So dEz is how much? dE sine phi with a negative sign. So dEz will come to be minus k lambda dl by r square sine phi. And of course dl will be r d phi. So dEz will be minus k lambda r d phi by r square sine phi. 1 r will get cancelled away. Okay. Now if you need to find the total electric field on the z-axis, so the total field on the z-axis will be dEz. So it will be minus k will be taken outside, lambda will not come out, r will come out, and what is left is sine phi d phi. Now since lambda is not a constant, it won't come out, so we have to put lambda as a function of the azimuth, which is given in the problem. So this is given how much? Minus k by r lambda naught cos phi sine phi d phi, correct? So we'll get minus k lambda naught by r, and what is left is sine phi cos phi d phi. Now we can put the limits of phi. Now let's see what will be the integral of sine phi cos phi. We have two skills for this thing. One is the theorem of function with its derivative, and one is what we can convert. We know 2 sine phi cos phi. 2 sine phi cos phi is sine 2 phi. Number one, first property. Second property, we know integral of sine 2 phi d phi is minus cos of 2 phi divided by 2. That is a basic integral. Sine 2 phi will have an integral minus cos 2 phi. Now we have to further divide by the coefficient of phi, that is 2. Okay, so what we can do here first, I am doing this integral here. Sine phi cos phi d phi. I am multiplying and dividing by 2. So I'll get 2 sine phi cos phi d phi by 2. So I'll get half 2 sine phi cos phi can be written as what? Sine 2 phi d phi. Okay, now I will apply this property. So this integral will come how much? This integral will come to be half of minus cos 2 phi by 2. So I'll get minus 1 by 4 cos 2 phi. This will be the answer. So I can directly write this answer here. So therefore Ez will come to be minus k lambda naught by r, and this thing will come to be minus 1 by 4 cos of 2 phi within the limits how much? From 0 to 2 pi, correct? So you will get as what? K lambda naught minus into minus will be plus divided by 4r cos, put the higher limit. So 2 into 2 will be 4 pi minus cos of 0. Got it? This will be your answer. Now you know what is the value of cos 0 will be your value of 1. Cos 2 pi, we know cos 0, cos 2 pi, cos 4 pi, any even integral of pi. That is, you can write cos 2n pi, n belongs to integer. It has a value of 1. Got it? Any even integral of pi, cos has a value of 1. Got it? So this will come to be k lambda naught by 4r. 4 pi is the even integral of pi. So cos will be 1. Cos 0 we know 1. So answer will be 0. There is no z component. So the total field will be now, since there is no z component and the field can only have z and y component. So the total field will be Ex square plus Ey square whole under root. The total field will become to be magnitude of same as modulus of Ey. So your answer will be k lambda naught pi by r. This is your answer, and it is coming to be along the negative y-axis. Okay, so this is your answer. This is the field at the center of the ring. This is the field at the center of the ring. K lambda naught pi by r, and if you're taking a reference line, where we have taken the reference line, I guess upward y-axis. So your net field, if you're measuring phi from this vertical reference line like this, this is the model we have taken. So your net field at the center is like this along the negative y-axis. We have to simply, in the Irodov problem, we simply need to find the magnitude, but I'm also indicating the direction. So this is the net electric field at the center, and this field is in the plane of ring only, correct? There is no component of the field perpendicular to the ring. So this is your answer to part A. The field at the center of the ring. This is your answer to part A. Now we'll go for part B. Got it? Now let's see part B. In the part A, we have found the field at the center of the ring. In part B, we will find the field at any point on the axis of the ring at a distance x from the center. And as I told you, part A can also be considered as a special case of part B, taking x is equal to 0. Okay? So what you can do, you can also start with part B, and then instead of doing part A separately, you can just put x is equal to 0 in part B. So let us say we have a ring, and the plane of the ring is taken as the yz plane with the center at the origin. So I'm taking the ring in yz plane. You can take any plane, but since x is the distance given along the axis of the ring, so just to maintain some sophistication, I'm taking x-axis along the axis of the ring. Okay, so this is the x-axis, and a skill I already told you a bit earlier how to take the 3D component. Okay, this is x-axis, and say this is y-axis, and this is z-axis, and we have to take one element dq at an azimuthal angle phi. So this angle is phi, this angle is azimuthal angle in the plane of the ring, and this angular width is d phi, as I told you a bit earlier. That's why I told you the skill ahead. And this is angular position is phi, linear position is L, and the linear width is dl, and the linear charge dl has a charge dq. So you can write dq as what? Lambda dl, and dl as what? R d phi. So therefore dq will be what? Lambda r d phi. Let it be equation number 1. Okay. Now where is the target point? The target point is on the x-axis at a distance x from the center. Okay. So O dash is the axis. Okay, this we are taking as O dash. So let it be simply O dash is the point on the axis of the ring at a distance x from the center of the ring. Okay, now see, when you want to make the field at O dash due to this element dq, this element dq can be treated like a point charge, correct? So if you are making a top view, if you are making a top view, you will have a figure like this. As I told you in the previous segment, how to make the electric field. So this is y-axis, this is z-axis, and x-axis will come out of the plane of the paper, and this is your elemental charge with azimuth phi and angular width d phi, and this is a point O dash, and this charge is how much? dq. So what do you think? This dq will make a field at O dash. Let the field be dE. So we know the basic. When you make the field, this dq will be treated as a point charge. So we'll make a line joining dq with the target point, and your vector dE will be along this line, correct? Your vector dE will be along this line. This is your vector dE, correct? Now what will be the magnitude of vector dE? So this is a right angle triangle. Clearly you can see this is a right angle triangle. Let this center be C. So I'm making a triangle. Which triangle? O dash C, and this is say A, and this is what? The radius of the ring, and this is X, and this will be R square plus X square, and let this angle be phi. Sorry, phi is the azimuthal angle, let this angle be theta. So theta is the angle subtended by the line AO dash with the plane of the ring, correct? Angle subtended by AO dash with plane of ring, that is YZ plane. Got it? Now tell, and phi is the azimuthal angle. Now tell me one thing, as we did a little bit before earlier, if your dq is changing, because there will be tremendous number of dq, they will be continuous in nature on the ring. So as dq is changing, for each phi dq will change. As phi will be changing, dq will be changing. So when dq will be changing, phi will be changing. That means phi is a variable. Your azimuth is a variable which will run between 0 and 2 pi. But do you think theta will change? This angle is theta, correct? You won't see theta in this figure, as we discussed before. So do you think as dq is changing on the ring, circumference of the ring, theta will change? No, theta will not change. The orientation of that line joining dq with the point on the axis, that orientation will remain the same. So theta is basically what? Theta is a constant, correct? Now what will be the magnitude of dE? So dE will have a magnitude Coulomb's constant K dq divided by r square. So we'll get dE is equal to K, and what is the dq? Lambda r d phi by r square. Let it be equation number 2. This is your dE. Now we have to take the component of dE, as we did in the discussion of the skill needed for this problem. So I can make a plane parallel to YZ plane, correct? And this is a line AC. So I can make a line here. Say there is a point A dash above A and O dash is above C. So if this angle is theta, so vector E will make angle theta with YZ plane being the corresponding angle. So this component, the vertical component, will come to be dE sine theta, and the horizontal component will come to be dE cos theta, correct? As we did in the skill. The only difference is in the skill I taught you for a discrete point charge. Now instead of the discrete point charge, we have an elemental charge dq. If you see in this figure, so you will say this component, which one? dE cos theta is the component in the YZ plane. So this will be like this. This is the component dE cos theta, and this component is coming in the xy plane, so I can name it dE xy. And dE sin theta is coming along the x-axis. Sorry, not dE xy. This component is coming in which plane? YZ plane. And this component is coming along the x-axis. How much? dE sin theta, which I am writing as dEx. So we got the two component dE cos theta in the YZ plane. We got the two component of the electric field. One is dE cos theta in the YZ plane, that is plane of the ring, and another is dE sin theta along the x-axis, that is perpendicular to the plane of the ring. Now if you see, where will be the component dE cos theta? It will be below the vector. It will be below the vector dE. And as I told you earlier, this is a charge. If you are making its field by keeping the pen, so I told you in a very detailed manner, The pen will be kept like this, tilted, and the pen will make an angle theta. Pen will make an angle theta with this plane. So your shadow will be just below the pen. So if this azimuth angle is phi, so this angle will be phi, vertically opposite angle. Now you can write all the three components of the electric field. So your dEx, directly you got dE sine theta. Now what will be Ex? Integral of dEx. That is integral of dE sine theta. And what was dE? So dE was your k lambda r d phi, k lambda r d phi by r square. So we'll get k, and lambda will not come out of the integral. It is the value of cos phi r d phi divided by r square. Yes, r is a constant because r is what? R square plus x square. So this will be taken out of the integral. So we'll get k lambda naught r divided by r square. What is left is cos phi d phi, phi 1 0, and last azimuth limit is 2 pi, and the integral of cos is sine. So we'll get k lambda naught r divided by r square sine phi within the limit of 0 to 2 pi. So you will get Ex as k lambda naught r divided by r square. We'll get sine 2 pi minus sine of 0, and we know sine n pi, n is any integer, is 0. So sine 2 pi will be 0, sine 0 will be 0. So Ex will come to be 0. Correct? So there is no component of the field along the x-axis. So there is no component of the field along the axis of the ring. One thing is clear. Okay, now let's see the y and z component. Now for finding the y and z component, we have to take the further projections, because dE cos theta is neither the y component nor the z component. dE cos theta is the component in yz plane. So this is your z axis, this is your y axis, and in this plane we have a projection dE cos theta, and this angle is phi, and phi is a variable which is changing for each charge element. So I have to take the component of dE cos theta on both the axes. So this component will come to be dE cos theta, the length of the vector, multiplied by cos phi, and this component will come to be dE cos theta, the length of the vector, multiplied by sin phi, and this is what your dE y, and this is what your dE z. Okay, now let us find dE y. So I'm getting dE y as minus, it is on the right side, positive y is left side, dE cos theta cos phi. So I'll get minus, and what was dE? We got from that equation, dE was, I guess, how much? K lambda r d phi by r square. K lambda r d phi by r square. So I'll get, instead of dE, I can write k lambda r d phi by r square cos theta cos phi. Okay. Now what we can do, you can write, it implies that Ey is equal to, dEy is equal to minus k lambda is lambda naught cos phi r d phi cos theta cos phi divided by r square. Now what will be Ey? Simply the integral of dEy. So in the integral there are constants which can be taken out, k lambda naught r, and theta is a constant, already we have discussed cos theta, and small r is also a constant. What is left is cos square phi d phi. Now we can put the limit of phi, azimuth running from 0 to 2 pi, correct? So this is the limit of the azimuthal angle. Now already we did this integral right back in part A, correct? So this integral we have seen from phi 1, so phi 2 has a value of half phi plus half sine 2 phi. This value is the integral, correct? That was the value of the integral. So what you can write? Ey to be minus k lambda naught r cos theta divided by small r square half phi plus sine 2 phi by 2 within the limit 0 to 2 pi. So Ey will come to be minus k lambda naught r cos theta by r square multiplied by half. Now put the limit 2 pi minus 0 plus half, I am writing a little bit here, sine 4 pi minus sine of 0, and we know sine 4 pi will be 0, being an integral multiple of pi, sine 0 will be 0 and 2 will get cancelled away. So I'll get Ey to be minus k lambda naught r cos theta, correct, divided by into pi divided by what? R square. Now you can put the value of cos theta and you can put the value of r. So cos theta we can find from the right angle triangle. That was the right angle triangle, correct? This is A and that point is O dash. This is C and this is R and this is X, and this was R is what? R square plus X square under root, and that angle was theta. So cos theta will be base upon hypotenuse. So you'll get Ey is minus k lambda naught r by small r square pi, and what is cos theta? R divided by r square, or you can write simply right now small r. So we'll get r cube, correct? So we'll get Ey as minus k lambda naught pi r square divided by small r cube. So we'll get minus k lambda naught pi r square divided by small r is r square plus x square root. Root means the power is half and there is 3. So I'll get what? 3 by 2. So this came to be the y component of the electric field. Okay, this came to be the y component of the electric field. Got it? Okay, what is left is now z component. Now what will be the z component? We got Ex is coming to be 0, Ey is coming to be this. Now what is the z component? Now on the z axis, what we are getting? On the z axis, we are getting dE cos theta sin phi. dE cos theta sin phi. So on the z axis, dEz, I'm getting minus dE cos theta sin phi. Put the value of dE minus k lambda r d phi by r square cos theta sin phi. Okay, so dEz will be minus k lambda is lambda naught cos phi r d phi divided by r square into cos theta sin phi. Now what will be Ez? Integral of dEz. So what are the constant? Minus k is a constant, lambda naught is a constant, r square is a constant, capital R is a constant, this cos theta is a constant. What is left is sin phi cos phi d phi from phi 1 to phi 2. Now this integral also I did in the, I guess, part A. You can write, you can multiply and divide by 2. So you'll get what? Sin 2 phi by 2. So this will come to be 1 by 2. And the integral of sine is minus cos 2 phi. Now further divide by the coefficient of phi, that is 2. So I'll get what? Minus 1 by 4 cos 2 phi. This is the integral of this thing, correct? So your Ez will come to be how much? So your Ez will come to be minus k lambda naught r cos theta divided by r square, and minus into minus will be plus because there is a minus, and I'll get what? 4, that is 4 cos of 2 phi within the limit phi 1 beginning with the azimuth of 0, phi 2 ending at the azimuth of 2 phi. Got it? So you'll get what? You will get Ez as k lambda naught r cos theta divided by r square 4. Now put the limit, you'll get cos of 4 pi minus cos of 0. Cos 0 is 1, and already I told you, if you take any even multiple of pi, you are writing cos 2n pi, n belongs to integral value. This will always be what? 1. Any even multiple of pi will have a value of cos. Even multiple of pi will have a value of 1. So Ez will be k lambda naught r cos theta divided by 4 r square. You will get 1 minus 1. So answer will be 0. So your Ez is also coming to be 0. So interestingly, out of the three dimensional component, 2 components are coming to be 0. There is no field along the z-axis, and there is no field along the x-axis as well. So you got what? Finally you got Ex and Ez to be 0, and Ey came to be how much? Minus k lambda naught pi r square divided by r square plus x square index 3 by 2. This is the answer you are getting. So of course your net field will be along the y-axis only, so in the plane of the paper. And if you want to find the net field magnitude, which can be written like this, so it will be Ex square plus Ey square plus Ez square whole under root. So already 2 components are 0, so it will be simply the modulus of Ey. So I'll get k lambda naught pi r square divided by r square plus x square 3 by 2. So this is your answer. This is the net electric field. Okay, this is the first answer. The net electric field at the axis is Coulomb's constant. K is of course your Coulomb's constant, which can be written in the last step as 1 by 4 pi epsilon naught lambda naught pi radius square by r square plus x square 3 by 2. And this field is along the negative z axis. Correct? So if you want to, though the problem is demanding only for the magnitude of the field, but if you want to make the direction too at the axis, so in this figure we have taken the coordinate system like this. Correct? That was the x-axis, this is the y-axis, and this is the z-axis, and the azimuth is taken from the y-axis, so it's taken as a reference line. So at a point P, the net field is coming along the negative y-axis like this. So this is the net field in this case. So you can see the net field is parallel to the plane of the ring. You remember in the case of a uniformly charged ring, which is a very common case in class 12th and most of the competitive exam, when the ring is uniformly charged. In the case of a uniformly charged ring, the electric field is along the axis of the ring. See the contradiction here. There is no field along the axis. The field is perpendicular to the axis. So net field is parallel to plane of ring. Got it? Okay. Then we have to investigate what will be the value of E when x is much greater than r. Correct? So we have to investigate. The problem is saying, I guess, investigate the obtained cases when x is much greater than r. So that is simply a mathematical approximation. So when x is much greater than r, so r square plus x square will approximately be x square. Correct? We can neglect r square. So your electric field magnitude will be approximated as k lambda naught pi r square by, now r square will be neglected and what is left is x cube. And you can put the value of k if you want, 1 by 4 pi epsilon naught lambda naught pi r square by x cube. This will be the answer. Got it? So this will be your answer when x is much greater than r. Got the point? Okay. Now you can cross check it. As I told you, part A can be obtained as the special case of part B. In fact, systematically we must do part B first, and then instead of doing part A independently, we can obtain part A as a special case of part B at center of ring. So at the center of ring, the value of x will be 0. So the electric field will be what? K lambda naught pi r square. Put x is equal to 0. So I'll get r squared 3 by 2. So I'll get r cube. So I'll get k lambda naught pi by r. See, you're getting the same answer. So instead of doing, for the center of the ring as an independent part, the wisdom is first to find at a generalized point x on the axis and then take the center as a special case and find its field by taking x is equal to 0. So this is the complete solution of all the parts of the problem 3.12, which is a very good problem. It needs a good amount of visualization in three-dimensional vector component. Got it?